Turns out the sun is a star. Thank you, Bill.
Thank you very much. So, good afternoon, everyone. Welcome from me and the Bison. I'll explain him later on, if I remember, but we'll just leave him there for the moment. Thank you very much to the SOC for inviting me to give a talk on a subject that's very, very close to my scientific heart. Back in the early mid-90s, when I was finishing up my PhD, which was focused on trying to detect oscillations in the bright star Procyon. I should add, I failed in doing that, so I started off my scientific career very much as a failing astroseismologist, and then pivoted to studying the sun. So for many years, I was very much focused on using sun as a star, observations of the sun's global core-penetrating P modes of oscillation to further our understanding of the sun's internal structure and dynamics, but also as well its activity, so the solar cycle. And that work I've continued. I did sort of pivot back to the dark side, to astroseismology in the sort of mid-2000s. That coincided, of course, with all the wonderful space missions we've had providing wonderful photometry, and that really has revolutionized astroseismology as a field, in particular Kepler. But the subject of the talk that I'm going to give is focusing on this question here. What can we learn about planet system characterization from observing the sun? So I'll try and touch on some of the key issues here. I apologize that I'm sure there'll be things that I miss. I apologize to people in the audience as well if I don't refer to your results. But I'll try and touch on, again, the key issues. Also as well, towards the end, I hope you'll indulge me, I'll spend a little bit of time right at the end talking about how we can use results from sun as a star helioseismology to actually address this particular question. Now, from the title of the slide, you can see a lot of this, of course, is pivots on the important privileged view that we actually have of our own star, the sun. So it's sort of, if I've said here, sort of referring to thinking about the sun as a star. How can we actually make use of all the wonderful plethora of data that we have on the sun, including resolved sun data, so highly resolved observations that, of course, we can bin down to make a sun as a star proxy, but using those data to understand what actually drives the variability on the sun, what actually makes up the content of the data when we observe the sun as a star and observe distant stars, and using those data to help us drive developments in analysis techniques and also modeling. And then, of course, there's actually then using actual sun as a star data to actually benchmark and test those methods of analysis. And also as well to help us understand when we actually observe distant stars, what can we actually learn from the data that we actually observe on them. So just to dig a little bit deeper then, thinking about going through the things that we can actually learn from observing the sun. Obviously something that some of the talks have already touched on today, Michael's talk in the last session about understanding the impact of variability of the sun, variability of stars, and our ability to be able to detect planets. Now, clearly this audience here, I don't have to go into the details of the importance of that. I'm preaching to the converted. Nice quote here, does the job. That's from the final report of the EPRV working group. And there are a number of you, of course, in the audience who were very actively involved in that. So thinking about the different drivers for that variability, the sort of big contributors to that, of course, there's the different scales of granulation that we have. Also as well, signatures of magnetic activity. Of course, that's linked to the granulation through stuff like magnetoconvection, but also larger scale stuff, large active regions, plage, faculae as well, which featured in Sarah's talk. Also as well, of course, stellar oscillations and different types of waves and also flows that I'll come back to later on. Of course, there's a subtle aspect here that the relative amplitudes of these different components varies depending upon how you actually observe your star. So, for example, whether you're observing in photometry or Doppler velocity. And then there's an added layer of detail there, how you actually go about making your photometric observation. So your wavelength bandpass will affect the relative amplitudes of these different components. Similarly, which spectral lines you're using as well for doing RV data. So that's a subtlety to bear in mind. Also, of course, then there's how this variability impacts on the actual planetary signals that you actually measure. So that then bears to the point of actually getting accurate inferences on the planetary properties that we actually measure. So using this, again, trying to understand what's driving this variability so we can actually develop methods to actually mitigate the impact of that variability for both detectability and also as well for accurate inference on planetary properties. Then next, of course, we've got using sun as a star solar data to help us test and validate as well the methods that we use to actually estimate the fundamental properties of the host star, which of course is very, very important. So how we can improve not only the precision in that, but also as well the accuracy. And then finally, just the sort of bringing all that together, getting a sort of holistic picture of the evolution of these systems, how the changing outputs, the changing emissions of the star influence the local environment where you have those planets, also as well mapping out the history and the future as well of those host stars, which also has a bearing then on thinking about the timeline of your planetary system, what's happening in the environment where the planets are, but also as well the dynamical evolution of planetary systems as well. So these are some of the things that we're obviously, we're concerned about here. Let's actually have a look at some of the data that we have for doing this. Now, I could spend all day going into all the different data products that we have available on the sun. I'm going to focus on just a few. I'm going to start with some examples of resolved sun data. Again, the importance of these data for being able to make really detailed images of the sun in radial velocity, looking at magnetic fields, also as well continuum intensity as well. So being able to, again, understand what's driving the variability of the sun. And then, of course, you can bin these data down as well to make a proxy for sun as a star data as well. I've focused here on instruments that are observing at the moment. A lot of similar instrumentation, which is no longer collecting data, which is producing or produce really, really nice legacy products that are similar to this. I'm going to start with this instrument in the middle here, which will be familiar, I'm sure, to many of you, and that's the helioseismic magnetic imager on the Solar Dynamics Observatory. So this is an instrument that is observing, producing RV data, also as well magnetic field data, continuum line intensity data, high cadence, high resolution. For the RV data, using an ion line, so a single line. So that's one other important point to make about how these solar data tend to be, so for dedicated solar missions, tend to be using just a single line. First, of course, using many, many lines that we have in stellar spectrographs. So that's a single line. That's producing wonderful data that, as we'll see, are being used for, again, trying to understand what's driving the actual RV variations, for example, when we observe distant stars. We've then got the GONG network. This is a ground-based network of helioseismology telescopes. So that had initially been the prime focus of that mission. The focus has sort of pivoted a bit more now on to space weather, but again, this is producing similar types of products, resolved sun, RV, magnetic field, and also continuum intensity, and going back to the 1990s. So that uses a line of nickel, again in the visible. The polarimetric and helioseismic imager is on Solar Orbiter. Solar Orbiter, which was launched fairly recently. It's also uses the same line as HMI and SDO, also same data products. The reason why I've singled this one out, this might be one that certainly towards the end of the decade may be very, very interesting to this community. And that's because the orbit of Solar Orbiter is basically going to see the spacecraft be cranked out of the ecliptic. So that by the end of the decade, it's going to have be something like 30, 35 degrees out of the ecliptic. So that's giving it a privileged view, basically, of the polar regions of the sun. So that's really, really important to get a better handle on granulation, magnetic fields and flows at the poles, which of course then will feed into some of the modeling and work on, again, looking at mitigating the impacts of variability. But also, of course, as well, it's giving us a view of the sun that we have of other stars as well. So, of course, pretty much all observations we've had of the sun have been from basically our vantage point actually in the ecliptic plane. So that's something, again, towards the end of the decade, it'll crank up to about 30, 35 degrees out of the ecliptic. I think these are data that you as a community really should be thinking about using. Then, of course, there are the several solar feeds that have been set up, dedicated projects to actually produce solar feeds into the very same spectrographs that are making RV observations of stars. And there are some posters on that as well in the poster area. Just to add as well, for HARPS 3, there are plans for a solar feed there to have a polarimetric front end. That's with the Aborus instrument, so Ben Lakeland has a poster on that. So using this combination of for example, the data from HMI on SDO, again, resolve some data to really understand and get into the detail of what it is that's actually driving the RV variability, and combining as well with data from these various feeds, that's producing a lot of outputs in terms of papers. So there are a lot of people, I was going to say several, probably many of you in the audience here, who are actually contributing to that work. So I've just picked out here plots from a few recent publications that are addressing some of these issues. Also as well, there's using solar observations as well to benchmark predictions from modeling. So a couple of examples here from MHD simulations. We've got an example down here of actually using MHD simulations to actually model the effects of RV jitter and the impact that magnetoconvection has on line bisectors. And then here an example of using an MHD simulations from the MURAM code to help understand the impact that small-scale magnetic fields have on limb darkening. Okay, so that has the predictions from that using solar data to actually calibrate those predictions, but also as well that has an important bearing then on potentially getting more accurate planet radii from transit data, and also as well for transmission spectroscopy observations. Here's one example of a data set that some of you might not be aware of that has had in the past a solar feed and will have going forward a solar feed with a polarimetric front end, and that's the Stellar Observations Network Group telescope, the Hertzsprung telescope in Tenerife. So this is a 1-meter telescope. Whoops, sorry. This is a project led by Aarhus University in Denmark. There are actually several nodes of SONG now around the world. So there's been one in China for several years, recently one that started collecting data in Australia, another that's being built in the US as well. So this 1-meter robotic telescope is actually been used an awful lot for astroseismic observations, but it has had a solar feed, solar front end, and as I said, there are plans to actually upgrade that going forward, so it will have actually a polarimetric front end to it. And then, this is where this chap comes in, the little furry guy, the little bison here. There is the Birmingham Solar Oscillations Network. So this is the project that I've been the PI of now for about 10 years. So this is a network of robotic telescopes that was set up in the 1990s. We actually have data actually going back to the 80s and 70s, 1970s even. But the network was established in the 1990s. And here the focus is on providing long-term sun as a star monitoring of the sun's oscillations, making RV observations with a 40-second cadence and having a network of observatories so we get near continuous monitoring. Okay, so we actually have one of our sites actually is at the nearby Mount Wilson. All of these sites located at places where we have high levels of insolation, so nice sunny places. Apart from, well, people who know Birmingham know that doesn't fit that description, but anyway, we'll skirt over that. So here are some nice pictures of basically 1 day's worth of residuals after the data have been calibrated. So what we can see here, the different colors are showing residuals from different sites. So it'll be sometimes during the day where sites at different longitudes are observing the sun simultaneously. So you can see some regions of overlap. The intrinsic precision here in each 40-second cadence at the best sites is better than 10 centimeters per second per measurement, okay? And so these data have been used, for example, so Michael referred to this paper here in his talk to help us calibrate some work we did with Heather and Chris on actually coming up with a recipe to do some intelligent, in inverted commas, averaging of the oscillations by choosing a suitable integration time depending on your fundamental properties of your star. Some other work that's being done at the moment by Federico Rosigno and Annelise Mortier, that is on doing a longer timescale calibration of the bison data. So our default calibration, because we're interested in the oscillations, really focused on stuff with a period shorter than 1 hour, we actually do our calibration 1 day at a time, and that imposes an intrinsic high-pass filter. What they're working on, along with two of my seismology colleagues, Guy Davies and Steve Hale, is to actually do a longer-term stable calibration of the data, which will basically open up being able to use the bison data for EPRV studies. And just to emphasize that potentially then would make available to this community over 40 years worth of data to play with, okay? One other type of wave or actual mode as well that one might want to worry about are Rossby waves, Rossby modes. So these are toroidal modes of oscillation that are formed by waves of vorticity from the Coriolis force. They've been observed in hot stars, A&F type stars. About 7 or 8 years ago, in resolved sun observations, they were finally observed on the sun by Laurent Guizon and his group at Max Planck. This particular paper, led by Nuccio Lanza, was working with Laurent on this paper, is actually producing predictions for a sun-like star of the typical sorts of signatures you might expect to see from some of these modes, so modes of different azimuthal order going down to m equals 2. And you can see that, in particular for the m equals 2 mode here, you get something that you could very easily misidentify as being the signature of a planet. Now, this particular mode here, this prediction for this mode is very uncertain because the m equals 2 mode has actually not yet been detected, but it's something that we're hoping to be able to detect once we get this longer-term calibration of the bison data sorted out. Okay, just to finish up, just to indulge me, we're going to do a little bit of seismology, so I couldn't do a talk without doing that. But just also to emphasize how we can use results from sun as a star helioseismology to actually get a real feel for what we can learn about the activity of stars and the influence that they actually have on their local environments. I'd said that the bison time base stretches back over, it's actually now back over 5 solar cycles. And what this slide is showing here is the seismic response of the frequencies of the modes. This is the frequency shift of the modes averaged over the most prominent modes as a function of time. And you can see there that the modes are basically essentially tracing out the solar cycle. So this signature here is actually giving you information on what's actually driving the solar cycle, the actual dynamo. It's giving you information on structural changes that are taking place beneath the sun. But what is also very interesting is that we now know that these data actually carry signatures that enable us to get a handle on the balance between spots and faculae on the surface of these stars. Something that we've done very recently is to actually ask the question, how short a data segment can we actually analyze, still get out reasonable measures of frequency shifts? So the previous slide there, I'd shown results from around about analyzing data in 100-day chunks. This is now analyzing data in 7-day chunks. And this is actually shorter than the rotation period of the sun. And we can actually see clear solar cycle variations. What this is now potentially allowing us to do is to actually see the seismic response of the modes to activity that's on the far side of the sun. And this opens up the possibility to be able to do that under the stars and to actually track on quite short timescales really, really strong emerging active regions and nest as they appear and disappear on other stars. The frequencies are not the only things that change due to the solar cycle. Also, the powers in the modes change as well. So the modes are actually, as Tim mentioned earlier, they're actually excited and intrinsically damped by the near-surface convection. So the fact that you actually see the powers change over the solar cycle provides you with a diagnostic of the properties of the granulation and how those properties are actually changing over time. So what the image on the right-hand side here is showing, so the dashed line here is essentially something like the sunspot number, so a traditional disk average proxy of the sun's activity, and the sun's frequencies essentially follow that proxy very closely. The data with the error bars are the changes in the mode powers, actually minus that. So as activity increases in the sun, the frequencies increase, but the mode powers decrease. Now, what's really interesting for the sun is that in the last cycle, the powers changed much, much more than you would have expected if the powers basically followed the changing trend in activity as described by the proxies, which is basically what the frequencies do. So that raises the question, what's going on here? Do we see this in other stars? What can it actually tell us about the granulation? And then the last thing I just wanted to cover is how we can actually use the frequency shifts of the modes to actually tell us something about the active latitudes on a star. So the idea behind this is that modes of different with different spherical harmonic characteristics, different angular degree L, and azimuthal order M, they will show a different response to solar activity depending upon how their spatial sensitivity, where the nodes and antinodes are on the surface of the star, actually map to where the activity is distributed on the surface. So what we did is we designed a method that we could apply to Kepler data. What we did is to essentially model the activity on a star as being basically an active latitude between lambda min and lambda max. And then what we did is to use the information from the relative differences in the frequency shifts of modes with different spherical harmonics to basically infer the lambda min and the lambda max, to basically do the inverse problem. So what we find for the sun is we get, so this is basically the posterior and the lambda min and the lambda max. So we get basically a lambda min of a few degrees essentially, so the value down here, and for lambda max about 40 degrees. If you actually use resolved sun observations of the distribution of strong magnetic flux, basically the values you get there basically agree with what you find if you look at how the flux is distributed on the sun. And it's that flux that's driving the change in the frequencies. So here's an example of applying this then to a solar analog, a solar type star observed with Kepler that has a rotation period pretty similar to the sun. But you can see here a very different distribution in terms of where its active latitudes lie. So pushed to much, much higher latitudes. And just to roll together the stuff I mentioned earlier about the prospects for actually being able to analyze the frequency shifts on stars in these very, very short subrotation timescales, here are the frequency shifts for that same star now measured with the 7-day data sets. Now, obviously, the data are much noisier than the stuff I showed for the sun, but nevertheless, if you actually do a statistical analysis of this, you see clear trends in the frequencies, even with these 7-day data, and also as well, the relative amplitudes of the changes in the different angular degrees here basically carry the same information as what we were showing here from our analysis all the way back in 2019. So with Plato coming up, Plato's due to be launched at the end of next year. We'll get the first sort of public release of data about a year after that, very roughly. And this promises to provide wonderful astroseismic data on the order of really high quality stuff on the order of something like 1,000 stars in the first long stare field. So I hope I've given you a bit of a sense of some of the important issues that are relevant to this. And at that point, I will finish. Thank you very much.
Thanks so much, Bill. All right, questions for Bill? I will start pointing at grad students if we don't get questions. Put your hand up if you're a grad student. Keep your hand up if there was anything in the talk that you're either curious about or didn't understand.
Hey, someone curious. Oh,
Right.
over there as well.
Zafar, ask what you were curious about in the talk.
That was cool. I was actually curious about everything in the talk, but I'm trying to limit myself. So why do you think the granulation might change with the solar cycle?
So there's some modeling work been done on that, which has focused on, so there's some evidence that maybe the aspect ratio of the granules changes over the cycle, so that you go from sort of, very extreme example, flat pancakes to cylinders, and that may have an impact. Some work I'd done, some of you in the audience may know the name Gunter Hudek. So Gunter had actually done some models of this, again, using flat pancakes at one extreme and cylinders at the other, which could maybe explain what we're seeing there. Yeah.
Oh, you have a follow-up? Go ahead.
Sorry. My follow-on to that was, do you know if the continuum, like optical images that you get from SDO, if they're good enough for you to actually look at the changing shapes of the granules over a cycle?
I don't know.
Thank you.
Honest answer, yeah.
Okay.
Oh yeah, lots of people nodding, yeah.
There we go.
Yes.
At the end, you talked about mapping the active latitudes. How many other targets is this possible for? Is it mostly limited by the magnitude of the target, or what's the probability of getting more in the future?
Yeah, so we need to be able to do that kind of analysis. You need to be able to measure frequency shifts, first of all, and so it's limited to the brightest targets, the ones where you get really nice seismic data. So I think there are still a number of them, and it's not going to be hundreds with Kepler, maybe a handful we might be able to do this. With Plato coming up, that number will increase. So I think we should I'm optimistic we'll get with Plato a statistical sample. And so a good coverage across the solar type part of the HR diagram with that, yeah.
Hi, I'm Steve Sarr. 173901, is that the high differential rotation, high metallicity?
Yes, it is. Yeah.
Right, okay. Yeah. What was the rotation period for that?
I think it's about 31 days, something like that. So long. A little bit similar to the sun, but maybe slightly longer.
Okay, yeah. And yet quite high latitude activity. That's very interesting.
Here?
Bill, I'm a graduate student, very interested in coming to Birmingham and for the weather. Anyway, so with Kepler, we started out by thinking the sun was a proxy for all the stars that are like the sun, and we found out that the sun was very nice compared to a lot of the other stars we observed. They were noisier. So can you make a prediction, or even go out on a limb further and tell us for real, what's the difference between the sun and all those stars? Will the sun eventually become that noisy? Has it been that noisy? Or is it just fundamentally different mechanisms between the noisier solar stars and the nice solar stars?
I'll probably answer that question maybe in a slightly different way and say that some of the stuff that I've talked about, some of the neat things I've talked about doing related to activity, it's easier to do on stars that are more active than the sun. So I think with Plato that will give us, because it'll observe very, very bright stars, it will give us the ability to do that stuff on the sun. But we've probably got to be a little bit careful maybe with some of the Kepler stuff, some of the really, really nice stars, the extent to which, particularly the stellar cycle stuff, we're biased towards stars that are more active than the sun because it's easier to see the variability, basically. So, yeah. And that's not quite answering your question. But
Can we thank Bill again, please?